In this video, I'm going to talk about friction force, and this is part one of probably 3 videos. And in this video, I'm going to talk about the type of friction force, and in later videos, I'll talk more about mechanism. And we are going to learn more about types of friction force in this video, but that's the major focus. So we're going to talk about 2 types of friction force. There are actually more, but we're going to focus on just 2 of them because they're the 2 that we are going to see most commonly. And the first type is the static friction force, and the symbol is you have an F for force, and then there's a lowercase f for friction, and then the S can be upper or lowercase, stands for static. And it's, if we think about friction force just in general, regardless of the type, it is the force applied between 2 surfaces that are in contact with one another at the surface where they meet. So in order to have friction force, the 2 surfaces have to be contacting. So whenever you have normal force, you are generally also going to have friction force. Often we will ignore friction, but the 2 go hand in hand. You really cannot have normal without friction, and friction does not exist without normal. But generally we're going to ignore friction, never ignore normal. So friction, force applied between 2 surfaces in contact with one another. Now, the static type of force means the object is not moving. So you can think of the roots of static, it's stationary, so not moving. And another thing that's important is that the direction of static friction opposes the direction of the net force if the friction were not there. And then the unit, like all forces, the unit is newtons, and the symbol is a capital N. So we're gonna, I've got a slide to indicate mechanism. All right, so I've drawn, all right, so let's look at our situation. We have the box. You've already done this on the PhET sim, so hopefully you understand a little bit more about it. So we have a box. It is 50 kilograms. And we have a man pushing, and he's pushing with a 50 Newton force. I know it says applied force. It's a normal force. And then there's a friction force because I've got 2 surfaces in contact with each other, the box and this ground floor. And at the surface where these 2 meet is where the friction force happens. So there is a red arrow. Okay, that red arrow is my representation so that you understand the direction of it is parallel or anti-parallel the direction of motion. And so just to emphasize, the friction force occurs at the surface. Now, the thing that's important to remember, though, is that when you are drawing a force diagram or free body diagram, we always represent the object as a dot. And so this would be the crate. We know that velocity is happening to the right, and so we would draw the friction force still on the dot, but going to the left. I do not have an arrow for velocity because this is a free body diagram. All I represent are forces. Okay, so you did some experimenting with the PhET diagram, or PhET simulation, so you know how it works. And so when the man applies 50 newtons of force, there's a friction force of 50 newtons. And then when he applies 100 newtons of force, there's a friction force of 100 newtons and still not moving. Okay? And hopefully you've all had this experience. You push against something and it doesn't move. You push harder, still doesn't move. So your push harder is being opposed by a bigger friction force opposing the motion or backwards. And so between these 2 surfaces, the strongest force that I can push without the box moving is 125 newtons. So the man pushes with 125 newtons. There's a friction force opposing the motion in the other direction, 125 newtons. There's still no speed, But the moment I get over that hurdle, what happens? I apply 126 newtons, the box starts moving. So I can see it has speed. It will actually increase moving. The speed will increase, it will accelerate. Another interesting thing has happened is notice now once the box is moving, the friction force is now 94 newtons. And so the last amount of force before it started moving, so this is the highest value of the static friction force, is 125 newtons. Now that the box is sliding, the friction force has decreased to 94 newtons, and we'll talk about that in just a moment. Okay, so a huge observation that we can make from this is that static friction is a variable force. Its size changes as the net force changes. So as I went from 50, friction 50. I applied 100, friction 100. I applied 125, friction 125. So the friction force varies. And in the lab experiment that you did with the blocks, we're trying to show that, but we probably did not have enough friction. Next year, I may use more friction. So you can see you can apply force and the box doesn't move. Okay, second observation. Once an object starts sliding, the friction force decreases and it becomes the other type of force that we are looking at. Now, this name has a huge misnomer. So it's called friction, kinetic friction. So once you start moving, and put this in quotes, we now have the kinetic friction. Oh, I misspelled that. Spelled correctly. Kinetic. Kinetics hopefully reminds you of kinematics, so study of motion. So we have kinetic friction force. Now, the reason why it's misnamed is because there are different types of motion. So I can walk, I can also slide on my feet, or a car can like skid, but it can also roll, okay? All of those involve friction. So when we talk about kinetic friction, we are talking about sliding only. And this is something you're just going to have to remember, is that kinetic friction, the motion is sliding only. Anything else, not kinetic friction. All right, so big thing, we're introducing FK, symbol F force, lowercase f friction, K kinetic. And another thing that we infer is that the force of friction kinetic is less than the force of friction static. Now, there are a couple of weird materials for which they are the same, but again, in the situations we are going to encounter, this relationship will always be true. Like I said, there are a few weird examples where they're equal. Kinetic is never bigger than static. All right, let's see if we can infer more. So we're going to look at the same experiment with static friction, only we're going to use twice as much mass. So I have two boxes stacked on top of each other. And I did the same experiment before. I kept increasing my applied force, and the box didn't move. I got all the way to 200 newtons. I had 200 newtons of friction force. The box didn't move. And again, hopefully you've experienced this in real life, that it's harder to get heavier objects into motion. You have to push a whole lot harder. And so for the box, I was able to get the man to push up to 250 newtons, and the box still did not move. It's kind of interesting because I'm just going to point out with 50 kilograms, my force of friction max was 125 newtons. And now with 100 kilograms, my force of friction static, forgot to put an X on that one, max is now 250 newtons. That's kind of interesting, wouldn't you say? Okay, just a little aside. All right, and now the moment I get to 251 applied force. The box starts moving, so I can see that it has speed. And my friction force has dropped to 188. That's also an interesting value. Okay, I'm just gonna write here. So when mass was 50 kilograms, we had the force of static friction was 125 newtons, and the force of kinetic friction was 94 newtons. Now that we are at 100 kilograms, the force of static friction is 250 newtons, and the force of kinetic friction is 188 newtons. I wonder if we see a relationship. Okay, so when we had twice as much mass, what we observe is that the force of static friction is now twice as big, and kinetic friction is also twice as big. All right, so what happens if we do 3 times as much mass? So I'm going to put on the garbage can, which is 100, and my crate is 50, so I now have 150 kilograms, which is 3 times as much mass as I had originally. And I can apply 350 newtons, speed 0. I can apply 375, speed still 0. But the moment I get to 376, my speed starts increasing, and my force of kinetic friction stops. Okay? So 3 times the mass, force of static friction 3 times as big, force of kinetic friction 3 times as big. So it seems like normal force, at least on a flat surface, is related to the mass. All right, we're going to do another experiment. This is our last one, in case you're getting bored. So I had all of the trials I did, friction was set right in the middle, which is the default, okay? And I found that my maximum applied force of static friction, maximum applied static friction was 125 newtons, okay? Then I turned the friction down, and I want to just point out what's happening. If you look really closely, you can see that when I was in the middle, this is what the surface looked like. When I turn my friction down, it smooths out. There's not as much kind of gritty stuff. If I turned it all the way down, this would be totally smooth, okay? So that's what friction is. It's a surface interaction, and it has to do with surface roughness. So at this level of friction, the maximum applied force or maximum friction force I can have before the object starts moving is 63 newtons, so less. When the surface is smoother, I can apply less force before I start moving because there's less static friction. Okay. So now I'm going to turn the friction up. And again, when I look at the surfaces, I can see there's a lot more like gritty stuff than there is when I was at the default setting. And if I turn it all the way up, you would see a lot more grit. Okay, so again, regular was 125. When I apply more friction, the maximum I can get to is 176 is my maximum static force with my maximum applied force. And as soon as I apply a little bit more force, then the object starts moving, and I no longer have static friction. I have kinetic friction or sliding friction, and the friction goes down. I don't see that because this is the maximum applied. Okay, so our observations. The maximum static friction depends on the roughness of the two surfaces. So it depends on the two surfaces that are in contact with each other. So if I could change either the surface or the object, either one. So I could put something very smooth on here, like a silicone, silicone is really slippery, or Teflon thing, and friction would go down. Or I can smooth out the surface, and friction will go down. So both surfaces affect the maximum static friction. Okay, so inferences. Both static and sliding or kinetic friction forces are related to mass. Static friction is a variable force. It has a maximum value before the object starts moving, and I no longer have static friction. And then sliding or kinetic friction is always less than static friction, except in, like I said, a few weird materials. So, formulas. First, we're going to look at something called the coefficient of friction. It has the symbol mu. It's a Greek letter. I'll draw it for you. It's like a U only with a tail, so it looks like this. That is mu. I'll do it one more time in case that was too fast. I'll do it slow. So you have a tail, goes like this and like that. So it's like a script U with a tail, but it's mu. And you have a different mu whenever you have two different surfaces. So mu is dependent on both surfaces in contact with each other, and there are tables of mu. There are things that will be given to you. Also notice there is no unit for mu. It's a coefficient. And then here are the formulas. The force of static friction. So force of static friction is less than or equal to, remember it's a variable force. There is a coefficient of static friction, so less than or equal to the coefficient of static friction times the normal force. And the force of sliding or kinetic friction is the force of friction, kinetic, that's the symbol for it, is equal to the coefficient of kinetic friction times the normal force. And then just remember the normal force. Normal does not mean natural. We've talked about this a lot. It's a reaction force. It's a push caused by electron clouds being squished closer than they want to be. We will, next time, we will talk more about how do you calculate normal force.